So now let's start looking off at the pressure velocity formulation. So I'm assuming that you have already done a fluid mechanics course, and so we'll just write down the Navier-Stokes equations and we'll see how to discretize them using FEM. And after we do that, then let's look at the concept of pressure as a Lagrange multiplier, and after that we can look at the other concepts like the PSPG or SUPG. So let's write down our Navier-Stokes. And first we'll just look at a very simplified case, which is Stokes flow. So this is your change in momentum, and this is your so we saw this term also coming in our scalar transport equation, right? And also in our total derivative. So this is your u dot del. So this is the scalar, and it is multiplied by this velocity, which is a vector. So u is your velocity, and once you integrate these equations over the volume, you will get units which are basically momentum upon time, right? Or you could also get the units of force basically, but we write this as a momentum balance, not as a force balance. So so this is your convective term, and then you have your divergence of stress, which is representing the effect of viscosity and pressure, and you have your body forces, okay, which is F. So in this case we are interested in laminar incompressible flows, which means we are interested in low values of Reynolds number, and Reynolds number is basically just your density into velocity into your characteristic length upon your viscosity, which is basically just the ratio of your convection to your viscous effects, right? So which means that we are looking at a case where these two terms are like equally dominant, or this term is just dominating, right? So the viscous effects are dominating. So let's look at the case in which we are just having Stokes flow, which means Reynolds number is equal to 0, and this term here. So this term is anyways discretized by using finite difference like techniques. So there is some finite elements which does trickle in, like the mass matrix, but really this term is discretized as an FDM kind of approach, with an FDM kind of approach. So we'll ignore this term, and this term will only come in when we look at the SUPG. So really we are just interested in this guy here right now, and we'll ignore the the body forces to make it simple. So let's just write this down. So this is our equation, right? Our Stokes equation over the volume, and let us represent this is our domain with a volume, and the boundary can be called as dV, okay? And of course along with this we have to solve our mass balance, which is our integral over the volume, change in your density with time, plus your divergence of. So we have already seen this mass balance as well as the convection diffusion, the total derivative, and these kind of concepts in the first bunch of videos. So really no need to repeat them here. So this is your mass balance, and we are interested again in the incompressible case, which means that your density is constant, which is representative of a lot of real world phenomena where the density doesn't change. So we can just take it as constant, and when we do that, this equation just simplifies to divergence free velocity constraint, which is a very famous constraint, right? So we just have to solve these two equations, right? So this is your first equation, and this is your second equation. So let's just write down our FEM discretization for this, and for doing this, let us just simplify the sigma term first. So sigma can be written as two parts. So this is your viscous stress, and this is your pressure. So if you consider a fluid element, so this can just deform almost infinitely, right? So that is why in case of fluids, we don't look at displacements, we look at velocity, we look at strain rates instead of strain, right? So this tau is basically your stress, and let's look at how this relates to your strain rate. So if this is your fluid packet, you could, and you're thinking of the force per area applied on this, you can just think of it as a normal force, but you could also think of it as a force which is acting tangentially. So all of this deformation really is accounted for in your viscous stresses, right? So these are basically mu, your viscosity, into your grad of your velocity into the transpose of that, plus your pressure, right? So your pressure is basically your thermodynamic variable. So we know that, I mean, you could just compress air and these molecules of air would just come together and they would get tightly packed, and then air would go from a gas to a liquid, right? So which means that this fluid element, so there could be a transport in and out by a pressure gradient, and so we have to know this quantity, and this is a thermodynamic variable. But in our case, in case of the density, this takes the effect of the Lagrange multiplier, and we'll see how this happens. So for this, let's just simplify our equation. Let's first write down the finite element formulation, and then we can go to the Lagrange multiplier concept. So this was our original equation, right? So so let's just simplify this. I think I made a mistake here. So this term is negative because pressure really decreases along with the transport. So this guy is negative, and so I guess I have taken this negative, so this will be positive. Okay. Right. So this is our equation. Because pressure is a scalar, so this is a gradient of that scalar, and this is again. So this will give you 1. So these are basically again your vector equations, right? And in case of your incompressible assumption, which is del dot u is equal to 0, this guy can be just simplified as mu del square u. So this simplification you might find in a lot of textbooks. So no need to do this here. So let's just use this and write down our simplified equation as mu del square u plus this is really getting okay. So let me just write this here. Okay. Right, so this is one equation, and your second equation is your del dot u is equal to 0, right? So these are our two equations. So since this is a vector equation, we'll have to dot with a vector test function, and this is a scalar equation, so we dot with a scalar test function. So so this equation we just dot with a vector test function v. So v dot and now once we integrate by parts, we'll just transfer this derivative here, and we would get grad v double dot grad u. This minus term will go away, and you still have your viscosity here, and this guy will become minus, right, is equal to. So this is your boundary term which arises from your integration by parts. So let's just write this down as your sigma, your stress, dotted with the unit normal in the outward direction, and let's dot our test function with this. So this is our FEM formulation, right? And this is our test function, this is our trial function, test function, trial function, test function, trial function, right? So let's just write this down again. So u can be written in your FEM discretization as a linear combination of some coefficients into your vector test functions, right? Because we are using the Galerkin's case, and in the Galerkin's case, your test functions and trial functions are the same. So you have this guy, and then you have your pressure, which can also be written as a linear combination of, let us say, some other coefficients into your pressure test function, right? So your pressure test function is Q, and so your continuity equation is just Q into, which is your pressure test, multiplied by your del dot U. Okay, so we have to understand how this guy comes here. So why does the pressure test function come here? And we'll understand this once we look at the equivalence with the Lagrange multiplier concept. But really, when we look at the finite element formulation, so this is our formulation, right? So in which you have your pressure test function multiplying with your continuity equation, and you have a divergence free velocity test function multiplying your pressure. Okay, so this is your finite element formulation, and as you can see that once we discretize this u as a sum of these trial functions, so this term will really be symmetric. So which means that once we try to do this, expand this into a matrix, you will just get these trial functions as your columns, and your test functions will be your rows. Okay, so let's look at this a bit later. Let's complete first our Lagrange multiplier concept, and then we can look at these matrices, each one of them. So we can look at this matrix, which is basically symmetric. These two guys are not symmetric, but they can be just expressed as a transpose, and then you get a nice saddle point problem with a null matrix. So we'll look at all of that, but first let us clarify why you have your pressure test function here, right? So let's do it by looking at the concept of the Lagrange multiplier.